Welcome to the video that's going to be talking about the typical reactions that can happen at that alpha carbon of the carbonyl. Specifically, we're going to be talking about halogenation at the alpha carbon, both starting with ketones and carboxylic acids, and also we're going to talk about the haloform reaction. The first reaction is called alpha halogenation, and we're going to talk about acidic conditions to start. So in acidic conditions, we can have ketones or aldehydes undergo alpha halogenation, which simply means that we add a halogen to that alpha position. This works with chlorine, bromine, and iodine, but will not work with fluorine. Recall that in acidic conditions, we're going to be using the enol reactive intermediate, not the enolate. We need base for that. So in acidic conditions, we're looking at the enol. So in acidic conditions, the first step for alpha halogenation is going to be protonation of the carbonyl oxygen. So we end up forming that enol, and it has resonance stabilization, just like we've heard before. Finally, we have the conjugate base, or the water molecule, pull the proton off, generating the enol form, which is what we're going to use. The second part of this reaction is going to be the halogenation. And so knowing that that carbon is nucleophilic, and that is going to reach out and form a bond with the bromine. Then we're going to follow that with proton transfer, giving us our alpha bromine product. When you have an unsymmetrical ketone, then halogenation is going to give us a mixture of products. We can, however, predict the major product is going to be the more substituted alpha carbon. This right here is, of course, tertiary, and this is secondary. So the tertiary is more likely to happen. And that's because in the enol form, that's the more stable alkene, the one that has the double bond with the more substituents. So another thing that we can use alpha halogenation for is as an intermediate in a two-step method to make an alpha beta unsaturated ketone. So you can imagine once you add that halogen here, then you can easily do an elimination reaction, giving us the alkene here, which then becomes an alpha beta unsaturated. In this case, we've used pyridine, but you can also use T-butoxide. The next reaction I want to talk about is called the Hell-Volhard-Zielinski reaction, the HVZ reaction. And this is a reaction very similar to what we've just been talking about, but this time now our starting material is a carboxylic acid. So in the same way that we added bromine to the alpha carbon of a ketone, we can add bromine to the alpha carbon of a carboxylic acid with these reaction conditions. We're going to use Br2, PBr3, followed by treatment with water. And so the way that that happens, this is an old reaction that we're familiar with, right? So PBr3 reacting with a carboxylic acid is going to give us the acyl bromide here as an intermediate. So then what happens is that this becomes an equilibrium with the enol form of that ketone. And so we end up with this acid halide enol. We react that with Br2 and we end up getting a bromine at that alpha position right here, followed by treatment with water, and we're going to convert that acid halide back into the carboxylic acid. And so then we're good there. Alpha halogenation can also be achieved under basic conditions. Okay, so remember, under basic conditions, we're forming the enolate as the reactive intermediate. And the reaction mechanism is shown here. So we're going to deprotonate, forming that enolate right here. Now that enolate is going to be our nucleophile to react with the bromine, and then we end up with our halogenated product. Under basic conditions, however, we can get multiple halogens adding, and we typically do. Once the ketone is brominated, it's more reactive, and so then we get it even faster and faster moving forward. So now we can take this idea even just to the next step, which is called the haloform reaction. So the haloform reaction is a reaction where we have a methyl ketone and we undergo this reaction at the alpha carbon in base, and we add 3 bromines to this spot right here. And then that group will leave. I'll show you the mechanism in just a second. That group will leave once we treat it with water, and then we end up getting back to our carboxylic acid. So it's kind of neat because the side product is actually something that we can use. So here's the mechanism for that reaction. We add our 3 bromines to that carbon. Then we have the base, attack the carbonyl, kick up, kick down, kick out this halogenated carbon, which actually, once we protonate that in this next step, so once we protonate that, we end up getting the bromoform here. We can get chloroform. In general, this is just called the haloform reaction. And then our organic product is going to be the carboxylic acid. This works with bromine, chlorine, and iodine, does not work with fluorine. And so this is a very useful way to produce carboxylic acids from methyl ketones. So it works best if our alpha carbon does not have any other alpha proton. So just the methyl ketone has all three there, and then the other side doesn't have any available. So then it's just more straightforward. So that's what we have for this section of this module. Enol, enolates, of course, and then the reactions at that alpha carbon. Now in the next section, we're going to be using that alpha carbon in an even more unique way. So stay tuned.